So hello and welcome to NHP's webinar on hazardous area motor protection. So my name is Thomas Krajinovic and I'm a commercial engineer for NHP Electrical Engineering, specializing in safety, sensing and hazardous area equipment. So this is the second in a series of webinars created specifically to inform you about hazardous areas and hazardous area requirements, with this presentation focusing on motor protection within a hazardous area. Now you see in the window that there's a Q&A section box there, and you're more than welcome to post any questions you have at any time during the presentation. And these will likely be answered as we continue through the presentation by our support staff, but we'll also have some time at the end of the presentation just to address these questions, as well as any others that you can think of at the end. So in this session, we'll be exploring the most common types of EX-rated motors that exist, and covering the general and additional requirements of the protection of these motors based on AS NZS 60079.14, which is the standard that covers installation and erection of hazardous area equipment. So what we'll cover today will be an in-depth look at what we need to do to ensure motors comply with the installation standards and they don't become a source of ignition within a hazardous area. So just breaking down what we'll cover, we'll just go over why we require EX-rated equipment. And doing this, we'll briefly look at hazardous areas as a summary to better understand this. And then we'll look at the commonly found EX-rated motor types in industry, followed by going through the detail, the general requirements around motor protection within a hazardous area. And then we'll go into the detail around additional requirements based on the specific EX protection methods according to the installation standard. Now, if you recall, in our previous hazardous area fundamentals session, we covered this in depth. If you haven't had a chance to see it yet, I recommend watching it after this, and it's available on the NHP YouTube channel. But just to quickly cover off on hazardous areas before moving to why we need hazardous area rated motors and the types that we commonly see. So hazardous areas exist in many industries, in areas of storage, processing and handling, from grain through to sewage and chemical. Now these areas need certain conditions for combustion to occur, shown here by the fire triangle and dust pentagon, where effectively you need all of these conditions to be present for combustion to occur. There is more to this though, and there are multiple properties of materials which affect how they behave and how likely they are to undergo combustion, which includes things like increased temperature of a material or environment, the energy available as a source of ignition, such as within a spark or through the surface temperature of a piece of equipment, as well as some physical properties of dusts. But luckily, all these factors are considered and grouped into certain properties known as the material groupings. So when we're looking at a hazardous area, the area is given a classification with the zone, equipment protection levels required, material grouping, and importantly, the ignition temperature of the combustible material. So then products are given ratings, which includes the material grouping and subgroup, and the temperature class, which is the maximum surface temperature a piece of equipment can get to, along with the other things like zone classification, EPL, and a protection method used by the equipment to ensure it provides protection within the explosive atmosphere. Now, the most important takeaway from all of this really is that you want to avoid your piece of equipment acting as a source of ignition, which is why we have hazardous area rated products. However, you still need to consider the use of the product and reaction to fault conditions, which cause things like heating acting as a source of ignition for some products, like motors, and we need to follow extra install protection and control conditions to prevent this. So electrical equipment is used in a hazardous area, and it must be certified for use according to AS 3000, clause 7.7.2.4.1, and AS NZS 60079.14, which is the installation standard in Annex 4.4. So according to these standards, equipment must not only be certified, but must conform to all the relevant requirements of the area it will be installed, and conform to the requirements of the protection method of the equipment and the type of equipment that it is. So motors are of course no exception here, and you'll find that there are many hazardous area rated motors that exist out in industry that require specific protection according to these standards. Now, the most common EX protection methods found for motors for use in hazardous areas are EXD, E, and N for when the motor is being used in an explosive gas and vapor atmosphere. And there's also EXT for when the motor is being used in an explosive dust atmosphere. Now, there are some general requirements for the control of EX motors that are presented within the AS/NZS 60079.14 standard. And for each protection method, there are also some special requirements for protecting the motor to ensure that the EX protection method being used by the motor is maintained and doesn't act as a source of ignition through sparking or heating of its surface temperature. So throughout the remaining part of the presentation, we'll discuss all these general and specific requirements for the various motor starting methods, such as soft starting, starting via variable speed drives, and mains connected starting. Now, the general electrical protection requirements that need to be followed are given in section 7 of the Design, Selection, Erection and Initial Inspection Standard, which was that 60079.14. And again, this details all the requirements for installing hazardous area equipment and points to other standards when required. Now, the purpose of all of these requirements is to ensure that the surface temperature of the motor is not exceeded. And if the surface temperature is exceeded past the T class of the equipment and temperature rating of the material within the environment, this could cause the atmosphere to ignite and an explosion to occur. Now, the surface temperature of a motor increases past its T rating when the motor goes into conditions where it begins to draw too much current and starts heating itself. So all of the requirements are here to ensure that any fault in the motor and its running does not increase the surface temperature of the equipment to this point of igniting the environment through overheating of the motor casing or causing a failure of the protection method through damage and heat, or again through sparking with a breakdown of the internals of the motor, such as the winding insulation. Now, these general requirements are focused around wiring protection and phase loss protection. So section 7 states that electrical circuits and equipment shall be protected against overload, short circuit and earth faults with the dangerous effects that these have on equipment, which of course is only made more dangerous within the case of hazardous area environments due to the heating acting as a potential source of ignition. Now, it details that you must use overload protection for electrical equipment if an overload can occur to the electrical equipment and the avoidance of this can't be guaranteed. Now, in this case, a standard thermal magnetic circuit breaker can be used here, as well as a separate earth leakage relay for the short circuit and earth fault protection. Now, these do not necessarily need to be hazardous area rated products, provided they are installed according to the standards, in which case you would either install these outside of the hazardous area, which may or may not be practical, or within a hazardous area rated enclosure, such as an EXD flameproof or EXT dust exclusion enclosure based on the area. Now, these devices would act to stop any short and earth fault conditions occurring, hence stopping excess heat being generated in the motor through the excess current draw, ensuring again that the surface temperature of the equipment is kept within its acceptable limits. And they would also stop any potential internal damage to the motor windings, which if damaged could cause further faults and sparking down the line. Now, this section also states that the short circuit and earth fault protection devices that you are to select and use, they cannot be auto reclosing while the fault still exists. So this final point, we're effectively stating that these devices and systems would need to be manually reset after the fault has been looked into. And if this was not done, you would find it would cause a dangerous condition and potential ignition of the atmosphere. Now, it's important to note that section 7 of the general requirements finally states that precautions shall be taken to ensure there is no operation of a multi-phase equipment where the loss of one or more phases will result in overheating. Now, this of course occurs in motors when there is a loss of one or more phases while the motor is running, resulting in overheating, again due to excess current draw. So in this situation, a phase loss relay could be used here, where the overload protection device on the motor does not have phase loss detection. And now, again, these would likely not be hazardous area rated and would be installed within the hazardous area within a rated enclosure, as I was mentioning before. Now, additional to the general requirements of Section 7, which cover wiring protection and phase loss protection, we also have further general requirements in 6079.14, focusing on rotating electrical machines, which we need to meet, as of course this is referring to motors. So within Section 7, 11, specifically 11.1, it states that additional requirements that rotating electrical machinery shall be protected against overload unless they can withstand continuously the starting current at rated voltage and frequency without inadmissible heating. So this just means they would need to be able to withstand the motor's locked rotor current continuously without excess heating. And it would mean that the motor would need to be rated to withstand stall and fault conditions like the one shown here, where the load is simply too large on the conveyor and it has stopped. And the ability to withstand the locked rotor current, it would come into the design of the motor, and this would increase the thermal mass of the motor to assist in dissipating heat to prevent the high surface temperatures occurring. But this would also increase the cost and size of these EX rated motors more than what they already are, which is why you don't often see these. So the fact is, the overwhelming majority of EX motors cannot sustain prolonged locked rotor current, and therefore they must be protected against overload. Now, in the case of a motor being used within a Group 1 environment, which is for underground coal mining or mines susceptible to fire damp, you are required to provide overload protection regardless of whether the motor can withstand the locked rotor current continuously. Now, Section 11.1 is then broken down into 3 requirements stating that the device used for overload protection shall be either one of the following or shall meet one of the following requirements. So Part A states that the device shall be a current-dependent time lag protective device monitoring all 3 phases set at no more than the rated current of the motor or the full load current, which will operate in 2 hours or less at 1.2 times the set current and will not operate within 2 hours at 1.05 times the set current. So as I'm sure you're aware, a standard motor overload or thermal trip circuit breaker is a current dependent time lag device, which can be used provided the trip curves comply with these requirements on the tripping times. And you would need to refer to the trip curves here just to determine that. Okay, now alternative to that, Part B states that the device shall be a device for direct temperature control by embedded temperature sensors. So this is effectively stating that the overload protection can also be provided by a device by direct temperature control by embedded temperature sensors or PTCs and thermistors. Now, most electronic overloads will have an option for PTC inputs. Otherwise, a separate PTC or thermistor relay can be used here as well. But this, of course, is provided that your motor has inbuilt temperature sensors for use in this purpose. And you'll find that most motor suppliers will have an option for this. However, it's not always present. So you would need to verify this on the motor because they can't be added later. You'd need to swap out the motor. Now, the third option, alternative to the other 2, Part C just states that the device shall be another equivalent device. So this could be any other device that can provide overload protection based on either direct or indirect temperature monitoring of the motor itself. Now, the idea here is to cover any technology that might not exactly have been invented yet for monitoring of the motor. But again, the whole idea is to ensure in all of these conditions that the motor does not overheat, regardless of the device or technology being used, so that you avoid the motor and its heat being a source of ignition to the surrounding hazardous area environment. Now, in essence, if the motor does not have embedded temperature sensors, such as PTCs or thermistors, a standard overload can be used depending on the protection method, as we'll see, but it must be sized accordingly. So there is a little bit of extra work that is required in the selection of the protection for a motor that does not have embedded temperature sensors, and care must be taken. Now, in most applications, getting a motor with embedded temperature sensors or PTCs is significantly easier to select for and is encouraged during the initial design stage. Now, this is especially true with reduced voltage or variable speed drive starting methods, the details of which we will be discussing shortly. So as mentioned earlier, so in addition to the general requirements of 60079.14, Section 7, and Section 11, which covers the rotating electrical machines, there are extra additional requirements for EXD, T, NA, and E motors within the specific sections of the standard shown here. So 11.2 for EXD, 11.5 for EXT, and 11.6 for NA. Now, these requirements are focused around using these motors in conjunction with converter supply and reduced voltage starting methods, so effectively for variable speed drives and soft starters. Now, luckily for these three, EXD, T, and NA, the protection methods, these have the same requirements, so we can discuss all of these together. Now, in the case of EXE motors, there are additional requirements for converter supply, reduced voltage starting methods, and mains connected starting, and these differ slightly from the other methods. And this is specifically the case for EXE motors when being used with mains connected starting, where the other protection methods need you to follow the general requirements mentioned previously. This protection method has additional requirements specifically addressing this use situation, and we'll go through that again in a little bit. So looking through the previously mentioned sections of the standard for the motor protection types, we can see that a variable speed drive or soft starter can be used to control an EXD, T, or NA motor, provided that one of the two following conditions are met. So the first condition is that the motor must be type tested with the specific variable speed drive or soft starter by the manufacturer, and this must be listed within its documentation. Second condition is where type testing has not been done, so direct temperature monitoring by means of embedded temperature sensors is required, with the effectiveness of the temperature control needing to take into account power, speed range, torque, and frequency for the duty required. And finally, the action of the protective device used for the direct temperature monitoring shall be to cause the motor to be electrically disconnected. These requirements aim to ensure that the maximum surface temperature does not exceed the specific temperature class on the motor nameplate to ensure the motor, as I've been mentioning, does not act as a source of ignition. So for the first condition, where variable speed drives and motors are type tested as a pair, as well as soft starters, they have been tested to ensure that the motor does not exceed this temperature under the normal use given in its documentation. Now, the normal use given in its documentation would include all details on settings and parameters required to be set in order to ensure the motor does not exceed this temperature. And if you were to deviate from these settings and parameters, you would not be able to guarantee that the motor will stay within the temperature class detailed on its nameplate. And effectively, you would be voiding the protection and this type testing and not meeting the compliance requirements. So this descriptive document would be part of the IEC EX certificate for the motor itself. And it would detail the model of the motor, the model of the drive that can be used, parameters that are used, and all of the limits that you need to stick to for the parameters to stay within the certification. Now, for the second condition, where type testing has not been done, the temperature of the motor needs to be monitored directly. Now, this is done by embedded temperature sensors in the motor windings, near the motor shaft, the motor casing, and any other place where they have a temperature sensor. And these sensors are designed around the temperatures expected at their locations within the motor and will cause their monitoring device to trip if the temperature exceeds their trip point. Now, the monitoring device, of course, would be anything from a dedicated thermistor relay through to an electronic overload with inbuilt PTC inputs, or add-on options for PTC inputs. So now EXE motors, they have their own requirements, like I was saying, given in section 11.3, that differ from the previous protection types. This includes differing extra requirements for EXE motors being used with variable speed drives and soft starters compared to EXD, T, and NA protection methods previously mentioned. While EXE also needs special overload selection and/or thermal monitoring for mains connected starting, which differ from the requirements we saw before as well for the other protection methods. And we'll go through this properly in a moment. So first, EXE motors can be used with the variable speed drive. However, there are a few differing points. So first off, there is no option for only direct temperature monitoring with a non-type tested variable speed drive. So where previously in the case of EXD, T, or N, you could use a non-type tested variable speed drive, provided you were directly monitoring the temperature of the motor. That can't be done in this case. So this means the only way you can use a variable speed drive and EXE motor is if they are type tested, and if they're a type tested pair with the specific variable speed drive by that manufacturer, and that drive is then listed in the IECEX documentation itself. Now, if this hasn't been type tested and it isn't there, then again, you just simply can't use it. You can't use direct temperature monitoring in this case. Now, with regards to EXE motors and soft starters, these can be used, and the requirements are the same as those for EXD protection protected motors, luckily, meaning that one of the two following conditions need to be met again. So the first condition is that the motor must be a type tested pair with the specific soft starter by the manufacturer, and this must be listed within its documentation. The second condition is where type testing has not been done, so you need to directly monitor the temperature of the motor by means of an embedded temperature sensor, taking into account again the power, torque, and frequency of the duty required, and finally the action of the protective device used for the direct temperature monitoring needs to be to cause the motor to be electrically disconnected. So as with EXD motors, these requirements aim to ensure the maximum surface temperature for the specific temperature class on the motor nameplate is not exceeded. Now for mains connected motors with EXE protection, in order to meet the requirements of section 11.1, which was the general requirements for rotating electrical machines, an inverse time delay overload protection device must be selected so that the following occurs. So first off, the motor current needs to be monitored, which of course a standard overload will do, but also a stalled motor will be disconnected within the time TE stated on the motor nameplate, and the current time characteristic curves giving the delay time of the overload relay as a function of the ratio of the starting current to the rated current needs to be known. And these curves will indicate the value of the delay time from the cold state for a range of starting current ratios, or the ratio between the initial starting current IA and rated current IN, known as the locked rated current. So this just means that the cold start trip curves of the overload protection device must be known, referenced, and compared with the details of the motor nameplate. Now also, the tripping time of the overload must be accurate to plus or minus 20%. So these are required as the longer the motor is allowed to sit in a stalled condition where it is experiencing its locked rotor current, the hotter its surface temperature will get, and hence is at risk of becoming an ignition source. So we want to stop this condition occurring at a time TE stated on the motor nameplate before the surface temperature exceeds the rated temperature class. Now below we have an example of an EXE motor nameplate that we've created, and you can see that there are two values required for overload selection towards the bottom right of the label. Now the first is the ratio IA over IN, which is the ratio between the initial starting current and the rated current, which is also known as the locked rotor current. Then you have the time TE, which is the maximum time at locked rotor current allowable by the motor before it will exceed its rated maximum surface temperature. Now, in this example, there are two values given for TE, which are actually prefixed with the temperature class the TE value is associated with. So from the temperature class T1, T2, we see a TE of 26 seconds. So this is for applications where the explosive atmosphere is classified as T2 or 300 degrees Celsius, and the maximum surface temperature of the motor must not exceed this value or risk ignition of the atmosphere. Now you will see that this time is longer than the T3 time, which is 200 degrees Celsius, as obviously 300 degrees allows for a higher surface temperature, meaning the motor can be allowed to experience its locked rotor current for a longer period of time before its surface temperature reaches this value. So the longer the motor is allowed to sit at locked rotor current, the hotter its surface temperature is. So for atmospheres with a higher ignition temperature, time TE can afford to be longer. Now in section 11.3.1, it states that the tripping time of the overload shall be accurate to within plus or minus 20% of TE, as we mentioned before. So when calculating and determining the maximum time the locked rotor current is allowed, it is of course common practice to be on the safer side and account for a 20% inaccuracy where the motor then must trip within 80% of the TE value on the nameplate. So due to this, we just need to consider the following new times, with this inaccuracy taking into account for the worst case accuracy scenario. So we'll consider the new TE times as 20.8 seconds for a T1, T2 environment and 7.2 seconds for a T3 environment. So if we begin to look through a selection example here, so we'll select an overload that meets the requirements of section 11 and 11.3.1. Now the first step will be to gather the necessary information from the motor nameplate and know your temperature class and supply voltage within the hazardous area, especially the supply voltage that will be provided to the motor. Now in this case, we can assume and imagine in this example that the supply voltage to the motor is 415 volts and we have an environment with a T3 temperature class. So if we gather the information from the motor nameplate, we'll need to obtain the following. So the full load current, or the IN, then the locked rotor current, or the IA over IN ratio, and then finally we need the TE value, or the maximum locked rotor time based on the temperature class T3 on the nameplate. So in the selection of the appropriate overload, the respective cold start trip curve must be referred to, and in doing so must ensure that the motor trips at 6.8 times full load current within 7.2 seconds, which of course is the locked rotor current of the motor we saw before, and 80% of the TE value that was on the motor nameplate, which we originally said was 9 seconds. Now it's just important to note that the red curve there is the cold trip curve. So that's what we'll be looking at there. And this figure is just a figure, or the trip curve figure of a Sprecher and Shoe CP7 electronic overload relay configured to a trip class 10. So now we need to see if the trip point required by the EXE motor is above the cold trip curve, or the solid red line. And we need to look at this as this is the worst case condition where the motor is initially cool and hasn't been running for some time. And obviously it would run the longest within a locked rotor current condition before tripping. Now, if we start by looking at the plane where the motor is at 6.8 times the full load current, and we draw that line there, and then do the same for the TE time constraint, taking into account the 20% inaccuracy, we can see that the trip point required by the EXE motor is beneath the cold trip curve. So we can see it's beneath that cold trip curve there. Now, having a closer look, obviously we confirm this, which means that the overload isn't suitable. So at 6.8 times the full load current, the overload will not trip within 7.2 seconds as required, And so in this particular situation, with this overload, this motor, and just this application, you can't use this overload. So if we begin to look at an alternative relay here, in this case, we'll look at the CT7N23C10, which is a thermal overload with the trip curve shown here. Now in this situation, we require a trip point, again, above the overload trip curve, which is the top curve labeled A. So if we begin to draw the same lines for the 6.8 times the full load current and the TE time constraint of 7.2 seconds, we'll be able to determine if this is suitable. And if we have a closer look, we can see that this point does in fact lie above the cold trip curve shown by line A. So at 6.8 times full load current, the overload will trip the motor within the 7.2 seconds as required, and therefore it satisfies the requirements that we're looking at of section 11 and 11.3.1. Now just note, this thermal overload has the capability of detecting a phase loss condition and will trip in less time as indicated by the lower curve there labeled B. So this just means that the relay also satisfies the general requirements of 7 for phase loss protection, and you'd be able to use this overload for this application. All right, so now it can be difficult to remember all of this, and if you were to just have these statements from the standards, it's a bit hard to remember. So we've created a summary table here, which it's easier to understand in its visual representation. But just reading across, so if we're using an EXE protected motor, we can see that if we're using a variable speed drive for control, we need to use a type tested VSD. Now the important symbols requirements, or the exclamation mark there, indicates that there are differences and things you need to take into consideration. So differences to the below other protection types. And there is no option for only direct temperature monitoring with this, with a non-type tested VSD, like it is possible with the other protection methods. Now, if we continue to move across, if we're using a soft starter with this EXE protection type, we can see that we can either use a type tested soft starter, or if we don't have a type tested soft starter, you can use direct temperature monitoring. Now, if you're using mains connected, if you move across and see that at the top, with EXE, you can use direct temperature monitoring, so that's okay. You can also use an overload. However, by that exclamation mark, the important requirement symbol, you need to be aware that, as we mentioned before, the overload must be selected in order to monitor the motor current and ensure that within a stall condition, the motor will be disconnected within the time TE stated on the motor nameplate. There's also the requirements about the accuracy of the overload as well, being accurate to 20%, as we mentioned. Now, when you're using EXD, EXNA, or EXT protection methods, we can see that if we're using a variable speed drive, we need to ensure we either use a type tested variable speed drive, or if we don't have that, when we're not using a type tested variable speed drive, we need to directly monitor the temperature of the motor. Again, if we move across, if we're using a soft starter for the EXD, NA, and T protection types, we need to ensure, again, we use either a type tested soft starter, or when we don't have a type tested soft starter, we need to directly monitor the temperature of the motor. And again, looking across to mains connection, if we're using a mains connected method of control for EXD, NA, or T protected motors, we need to ensure we use either an overload which trips within the specified times in the standard, or again, we can directly monitor the temperature of the motor. So the important requirement symbol is just here to remind you, to be aware that there's other things you need to consider. So you might need to look again potentially into the standards for that, but otherwise you can reference this chart. So this concludes today's presentation on hazardous area motor protection. Now, by now, you should have a greater understanding on the types of hazardous area motors present in industry and the general and specific requirements around control and protection of these motors to ensure that the motors don't act as a source of ignition through heating of the surface temperature. So I'm now able to answer any questions that you may have or have sent in during the presentation.
Great. So thanks for that, Tom. Great presentation. It was really easy to follow with a good mix of visual images to help break down at each point what you were trying to explain. So my name is Jack Wheatley, and I'm the product manager for safety sensing and signaling at NHP. So as Tom mentioned, we'll take this time to review some of the questions in the chat. So feel free, if you still have some, to enter them in, and we'll get to them when we as we move through the list. But we've got one here, Tom, that says, does NHP do any type of tested drives? Do you have any thoughts, or are you able to answer that for us?
Yeah, sure. So NHP, as far as I'm aware, don't actually have any type tested drives, but it's just important with that to note that this doesn't mean that you can't use any of our drives. So obviously we discussed depending on the depending on the protection method of the motor, certain conditions need to be met. So with all cases except for EXE protected motors, VSDs can be used provided you're directly monitoring the temperature of the motor. So if you have a motor with the misters, that's not EXE, then you can use any of our drives technically. Now, just another important thing to note is that it's actually the responsibility of the motor manufacturer to type test, soft starters and drives with their motors. So this would effectively mean that you would need to approach the motor manufacturer to determine, what model drives are suitable with their motors, and you just have to look at the hazardous area certificate. Now, if you are really set on using a particular drive and it hasn't been type tested and you really want it to, and you don't want to use temperature monitoring, there are actually test labs out there that allow you or do type testing for you with the motor that you're looking at and your drive or soft starter. So if you really want, you could approach them as well.
Great, thanks for that. So I've got another one here, and it asks, can I combine HAE and safety into one solution? That's a good question. What are your thoughts, Tom?
Well, yeah, it is a very good question, and you definitely can. So there are actually multiple products which are both hazardous area rated and safety rated. So we have a number of interlocks and solenoid interlocks from our suppliers that are used in these conditions. So it is possible. I was just going to say as well, it's also possible to use a product that's not necessarily hazardous area rated within the hazardous area, but that's provided it's classified as a simple apparatus, which just means it can effectively only have dry contacts, no circuit boards or anything like that. And you would then need to use this with a barrier to make sure that the dry contacts are suitable for use within the hazardous area. But you definitely can have products that combine both hazardous area protection methods and are safety rated as well.
Yeah, thanks for that. And definitely a very good question and something people need to take into consideration depending on the installation. So another one we've got here, where can I find the information for the calculations discussed in slides 21 and 22? Do you know where the customer can reach out, Tom, to find that information?
Yeah, so I think those slides were covering the calculations about EXE rated motors, connecting to mains, pretty much the calculations in regards to TE.
Yep, I believe so.
So yeah, that we actually have an application note that talks about, I guess, all of this, and it details that, like what you need to consider for that and how you go about selecting it with examples effectively. So really, if you are interested and you want to know more about that, I mean, there's this presentation that will go up on YouTube that you can refer to later, but we also have that application note that we could send out to you. You just need to either reach out to us now or reach out to us at a later date, through one of your sales reps.
Thanks for that. Yeah, a good point too. So definitely, if you do have any other questions along with requiring any documentation, please reach out to the sales reps. They'll be able to help direct you and point to the correct place. So we've got another one here. It's not a bad one. So do we always use the cold trip curve for the overload chart? Are you able to answer that, Tom?
Yeah, so you do have to, especially for obviously EXE, as we went through, because I mean, you need to look at the, like we looked at the current and the stopping time to make sure that, you know, in that situation where you're at the locked rotor current, at that time, you need to ensure that the motor stops. So you do need to look at the cold trip curves in that case. And that's obviously the longest case again. So that's where the motor hasn't, you know, been started, doesn't have any heat in it to begin with, and will experience that starting locked rotor current, you know, for the
Yep.
longest period of time.
Yep, definitely. No, thanks for that. So we've got another question here. Not an uncommon question either. I know plenty of guys would see things like this on a daily basis, but can NHP help make a selection of an overload?
So we definitely can, as long as obviously all the details are provided, you know, about the motor nameplate, and you know, you give us details about the environment, then yeah, we can definitely select equipment for you and help you in that case.
Great, thanks. So yeah, very good. Exactly. Feel free to reach out via your sales rep or through the NHP 1300 phone number if you do have any requirements or you need assistance on site. So we've probably got time for one more question, Tom. So I've got one here. Can I get a copy of that table? It's not really a question, but are we able to supply a copy of that table on your last slide?
Yeah, definitely. Again, obviously this will be available on the NHP YouTube channel. So, I mean, you can always look there and reference that. But if you do want this and you are interested, reach out to us or, you know, contact your local sales representative, and we can find the application note for you, which actually has that as well, that table in the end. So you get, you know, an idea on how everything works in that table to summarize. So we can forward that on to you as well.
Great, thanks. Yeah, and again on top of that, so we're pretty much out of time now. So I will just mention that if the presentation is going up on YouTube, but if you do have any additional questions, feel free to reach out to Tom or through your local sales rep. And thanks for joining in. But I'll pass back over to you, Tom, if you've got anything to finish with.
All right, thanks for that, Jack. So that is everything for today. So again, thank you for joining the webinar, and I hope you found it beneficial. And again, if you'd like to watch it, a recording will be uploaded to the NHP YouTube channel in a short while. Now, to find more webinars in this series, please go to nhp.com.au or to our dedicated NHP YouTube channel. And if you have any further questions about hazardous area, EX motor protection, please contact your local NHP sales representative. So with smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise. See you next time.